So firstly, gratefully thank the organizers of this workshop to give me a chance to report my work in front of experts. And I'm going to consider about p-valenced assertion schemes. Let's consider our discussion. Firstly, notation. Firstly, let us recall the definition of an assertion scheme. So X here is a non-empty finite set, and let S be just a collection of elements R0, R1 to Rd, be a partition of the Cartesian product X cross X, where we require that Ra is not empty set for all I belong to S. Each element of S is called a relation of S. Then S is an assertion scheme or briefly a scheme on X if the following conditions hold. We have three conditions. So firstly, the set of all pairs BB belong to X. This set is a relation of S. Usually, we will use R0 to denote this relation. Next one is so-called transpose relation. So for every RC belong to S, then there exists RC prime belong to S, such that for this relation RC, you flap for any pair in this RC, you flap the entries, you get another relation in S, which we use RC prime to deduce it. Finally, we have the intersection number. So for any Ri, Rg, Rk, which is in S, and the pairs Mn, M tutor and tutor in Rk, we have the following equality. So the number here equals the number here. And this equality can be used to define the intersection numbers. So here is the definition of an string scheme on a non-empty finite set. Continually, let us introduce another notation. So firstly, we fix a scheme S. S is just R0, R1 to Rd on a non-empty finite set X. Let Ra be a relation of S, and we fix X, a point of X. Set XRA is just you collect all B belong to X, such that XB is a pair of Ra. We fix a field F of a positive characteristic P. So P is a prime. Let K be the size of the set XRA. K is also called the valency of the relation Ra. And here we put SP. SP, what is SP? SP is just a set of all relations of RC whose valencies are divided by P. Let MXF be the full matrix algebra of F square matrices whose rows and columns are leveled by the elements of X. Here we let I means the identity matrix of MXF, G means the all one matrix of MXF, and O means the all zero matrix of MXF. Let EF be the 0-1 matrix of MXF, whose unique non-zero entry is in the EF entry. So if we collect all the matrices EJH, where JH belongs to X, we get an F basis of MXF. Continually, I want to introduce other notation. So consider about AA. AA just as matrix AAIG. AIG be the adjacency F matrix with respect to the relation RA. So AA just a 0-1 matrix of MXF, where AIG is 1 if and only if the pair IJ is in RA. Then we can define some algebras. So let S be the unit F subalgebra of MXF generated by A0, A1 to AD. It's called the modular adjacency algebra of S. Let RK be a relation of S, and we put ek star x is just the sum of all EYY, where y belongs to x or k. Fix the point x, so we can write EL star for EL star x for all are L belong to S. Let T be the unitary F subalgebra of MXF generated by A0, A1 to AD and E0 star, E1 star, ED star. It's called the modular trilateral algebra of S with respect to X. So here from the definition, T depends on the scheme, the field, and the fixed X. So this is the definition of the modular trilateral algebra of S. And we know that S is just a F subalgebra of T, because we know that for S, this is a generator, and for T, this is a generator. So S is an F subalgebra of T. Let G be the Jacobian radical of T. Since we know that the dimension of T is finite, so we can define this Jacobian radical to be the sum of all two-sided ideas, the nilpotent ideas of T. Continually, we need to define some modules. Firstly, SS. Let SS be the left regular S module because S is an associative F algebra with the identity element. So we can define this left regular S module by considering about the action of S acting on S by left multiplication. For a one-dimensional F linear subspace generated by V, we can define AMV just as the sum of KM copies of V's for all Rm belong to S. We can check that this gives us an S action on this F linear space. So this F linear space becomes an S module. Call this S module the trivial S module and note that it's unique up to S module isomorphism. We denote it by Fs. The scheme S is called a p-valence scheme if SP is an empty set. Now we consider about the thin radical. What is thin radical? Thin radical is just you collect all the relations whose valences are exactly 1. And the scheme S is called a coordinating scheme if for every RQ belongs to S over O theta S, the valency of RQ is just 2. So these are the notations. And now we consider about the motivation. Firstly, I want to mention a well point from repetition theory. So if we have some results for the scheme theory, we want to find the corresponding results of algebras and modules. And if we have some results in algebras and modules, we want to go back to scheme theory to find the corresponding results. So we want to get such a connection between the two fields. Let me introduce 2 examples. So firstly, let me introduce a theorem of Hanaki. He proves that for G, if G is just an auxiliary matrix, then S is a p-valence scheme. Because here G is just the Jacobian radical of T. So if G is an auxiliary matrix, then S is a p-valence scheme. So this means that we have a property here, and we get a property here. So from here, you can go here.
So that's a Jacobson radical over a field of characteristic P?
Yes, characteristic P. The field has characteristic P.
And J is the Jacobson radical of S. F, where F is of characteristic.
No. G is the Jacobian radical of T. the modular Terlager algebra, because we have fixed x.
Oh, okay. Yeah.
We have fixed.
Thank you.
So next, consider about another result. So here we have in here. So S is a p-prime valence scheme, and we want. So here is just because we have the trivial module and we have the left regular module, and we can consider about the S homomorphism from trivial module to the left regular module, and because this set can be built as an F linear space with respect to the addition of maps. So well, it is an F linear space, and we consider about the F dimension. So here, if you S is a p-prime valence scheme, then the dimension here is 1. It looks like a result of group theory. So if you have a group algebra, you have the left regular module of the group algebra, and you examine the home space, and you always have 1, because the left regular module here has a unique trivial submodule. And if you have S is a p-prime valence scheme, this is also true. A remark. The inverses of theorems 1 and 2 are not true. So if you are in here, you have a p-prime valence scheme, there may exist some x, some choice x, such as what you have constructed the modular Terlager algebra is not semi-simple. So the Japan radical here is not a all-zero matrix. And I can give some examples for this. If you are in here, you may not go here. And if you are in here, you can also not go here sometime. You may not go here. There are also a lot of examples that says that if you are in here, you usually cannot go here. So the two results motivates us to consider about the characterization of p-prime valence scheme. We want to have an if and only if for p-prime valence scheme. So results. Let me introduce the results. Firstly, consider about this if and only if condition. So the scheme S is a p-prime valence scheme if and only if for every RA belongs to the thin radical and M belongs to the Japan radical. Because this is a matrix, you can have EA star, this is a matrix. You can have M here is also a matrix. So for two matrices, you can consider about the multiplication. So this multiplication equals this multiplication equals the all-zero matrix. For every RA belongs to the thin radical, and for any M belongs to the Japan radical. And if you have this property for one modular Terlager algebra, you can deduce that S is a p-prime valence scheme. This is the if and only if condition. Next, so problem 5. A finite dimensional F algebra is semi-simple if and only if its Jack portion radical contains exactly its 0 element. So here we are interested in the following question. So find all true choices of the 3 tupes. So you have S, F, and X. For what S, what F, what X. The corresponding modular Terlager algebra is semi-simple. We are interested in this question because we know that for the modular adjacency algebra, we know for which case is semi-simple or not. But here, if you consider about modular Terlager algebra, we may not know these choices for these 3 tupes. And I remark that for coordinating scheme, if you have a coordinating scheme, then we know how can we choose here for coordinating scheme. But for journal case, we don't know. For journal case, we don't know. For coordinating, we know. For journal case, we don't know. Remark 6. By theorem 1, it's sufficient to work on p-prime valence schemes to solve problem 5. So if you want to consider about problem 5, we only consider about p-prime valence schemes. And theorem 4 may be helpful for problem 5 because we give a property for the Jack-Box radicals of modular Terlager algebras of p-prime valence schemes. So maybe helpful. next, we want to consider about a generalization of theorem 1. So let us give some lemmas. So firstly, for this lemma, for this Jacobi radical, and we consider about the f dimension here, and we can show that this number is larger than or equal to this number. Here, SP just the set of all relations whose valences are divided by p. So you have this 2 to the power 2 plus this 2, and you have the two numbers. And this result seems to be interesting because we know that for the Jacobi radical, it depends on the choice of x. So for different choices of x's, the number may vary. I mean, if you have two distinct x and you construct corresponding Jacobi radicals, the two Jacobi radicals may not isomorphic as F linear space. However, even if they may not isomorphic as F linear space, we still have this inequality. This inequality is always true. Lemma 8. So if P is 2 and S is a coexisting scheme, then we can get equal here. This should be, we will have equal here for any choices of x. So you have equal here. Moreover, we can show that for every m belongs to the Jacobi radical, m cube is a zero matrix. By lemmas 7 and 8, we know that this number is an optimal lower bound for f dimension of Jacobi radical G. Okay, so this is theorem 9, and let us use theorem 9 to prove theorem 1. So it's very easy. So if S is not a p-valence scheme, then the set of SP is larger than 0. And because we have this lower bound, so by theorem 9, the Jacobi radical is not all zero matrix, which contradicts our assumption that G is all zero matrix. G contains all zero matrix. This is a generalization of theorem 1. Now I want to mention Hanaki's approach for theorem 1. His approach seems to be very interesting. So let me introduce his tool. So for every RA belong to S, he defined EA star, T EA star, just as EA star, M EA star. Here M is an element of T. So you have a set. And we know that EA star T, EA star is a unital F subalgebra of T with the identity element EA star. Then he showed that T is semi-simple only if EB star, T EB star is semi-simple for all RB belong to S. So if you are in here semi-simple, you can get all this one semi-simple. However, he also have example to show that the inverse is not always true, not always true. Now, I want to consider about the following problem. This problem says that this problem is implicitly mentioned by him in his paper. So we want to find all choices of three tuples, S, F, and X, such that T is semi-simple, if and only if for all RA belong to S, EA star, T, EA star is semi-simple. So this is interesting because this looks like a local global things. So because we want to know the T is semi-simple, so this is a local property, but we can transfer it to the this is a global property, but we can transfer it to be a local problem to consider about all EA star, T, EA star. If all EA star, T, EA star are semi-simple, then we have T is semi-simple. So this problem is implicitly mentioned by Hanaki in his paper. And for this problem, we can see that for coexisting scheme, if S is a coexisting, for any choice of F and choice of X, this is true. So if T is semi-simple, if and only if this one is semi-simple for all I belong to S. So if S is coexisting scheme, then you have if and only if. other problems. So I want to mention other problems for this modular two-legged algebra. So we know that G is a nilpotent ideal of T. And so there is a positive integer such that MA is just an all-zero matrix for every M belongs to G. And we are interested in the following problem. So what can we say for this number? We know that if A just such a positive integer and assume that S is not a p-valenced scheme and MA is just an all-zero matrix for every M belongs to G, then we can show that A is larger than or equal to 3. So A cannot be 2 if S is not a p-valenced scheme. And we don't know that whether or not A can be 2 if S is a p-valenced scheme. We don't know. As our final problem, we found that the lower bound in Theorem 9 is always 0 if S is a p-valenced scheme. So it's not very good. If S is a p-valenced scheme, we want to find a non-trivial optimal lower bound for the F dimension of G. That's all. Thank you very much.
Thank you for your talk. And are there any questions, comments, remarks? Paul German, you should switch on.
Hello.
Is that better?
Hello.
Better now.
The first theorem of yours from 2021, can you display that again?
2021.
Your first own theorem.
Oh, first theorem. So first theorem is
When all
here. This one?
Can't see that is blocked. Now, if for all thin elements,
This one?
no results.
This one?
That one, yes. Right.
Yes.
Yeah. Okay, I just wanted to check what does the equation say if S is thin itself? It says that for every element in S, you have that ME star equals 0. How is that? Is that trivial?
It says that for every RA, which is in the thin radical,
Yeah.
and for any M belongs to G, I consider about the multiplication of the two matrices.
Product, yes. But I'm wondering if this equation is trivial, if the scheme S is thin.
Thin, yes. For good question. If you're thin means that the radical, the algebraic here is a all zero matrix. It's a simple algebra. If S is thin, then the modular two-legged algebra is simple. It's just a matrix algebra. So here is just an all zero matrix. So if you have any element here, you have any. This is a all zero matrix. So times is a zero matrix.
Oh, yeah. Okay. And if only the identity is so, if the thin radical is trivial, if you have
yes, trivial. Because we show that if S is a thin scheme, then for any possible choice of X, the corresponding modular two-legged algebra is just a one matrix algebra, M X size F. You can check, it's not difficult. Right. So you have a trivial radical and it times all the zero matrix.
Yeah. And another question, if there's still time. So you are always using the Jacobson radical of the Terwilliger algebra. What makes the difference?
Yes.
Why can't you work with the Jacobson radical of the adjacency algebra? Is it not enough information?
Firstly, for all semi-simple modular adjacency algebra, we know not simple, we know not semi-simple. And if you want to consider about the Jacobian radical for the modular adjacency algebra, it seems to be a little difficult.
Already?
Seems to be. I don't know, but I never considered about such question. But maybe I don't know whether or not it's difficult or not. But according to my feeling, my personal feeling, maybe a little difficult than the module Terreger algebra, because here, when that for these things, they have very nice computation rule.
Yes. Yeah, I see.
So, but if we have adjacency F matrices, so
right. Yeah. Yeah. Thank you.
Okay. Other questions, comments, remarks?
Oh, yeah. I still have another question, actually.
Yes.
So p prime valenced means that all valencies are p prime.
Yes, not divided by p.
Yes. You do not assume that the size of X is also a p prime number, right?
I don't assume.
So suppose you do. Do you get something interesting in that specific case? Maybe it's worth to look at that case, because that is a strong restriction also.
Yes, but so far I have never considered about such problem.
Yeah.
Problem seems to be interesting because
yes, I think it's a natural subclass of because if you define p schemes, then you also assume that all valencies are p powers, and also the size of X is a p power. So maybe it's interesting to look at that case.